Okay, great. So welcome back and good morning, everyone. So it's my pleasure to introduce Rolando Somma, who is going to tell us about quantum algorithms for linear systems.
All right. Okay. Thank you, Gary. Okay. So as Gurian said, I will talk about some work that I've been doing on quantum algorithms for solving linear systems of equations, systems of linear equations, and I'm coming from Los Alamos, a theoretical division. Oh, what happened? That's not a good start. Yeah, what is going on? Okay, there it is. And this is joint work with Robin Kothari, David Surci, and Igit Subasi, and Andrew Charles, that you probably know, who's here. And well, I mean, so as I said, I've been basically summarizing some of the work that I've been doing for this particular problem, but I think that one of the perhaps main impact of our work is on the techniques that we developed that could be used for developing other quantum algorithms as well. All right. There's a couple of references. My talk will be mostly based on this paper, where we exponentially improved the dependence on the precision for the HHL algorithm that you probably are aware of, and I will talk about. And then there's been some more recent work on quantum algorithms for the same problem, which are inspired by adiabatic quantum computing, but they could actually be implemented on the circuit model at the end. But the inspiration is from a Hamiltonian-based model, and it's actually turned out to be a pretty simple algorithm for the same problem as well. Since I know there's a broad background, I put a couple of slides for introducing a little bit of the history of quantum computing. So you probably are aware that quantum computers were mainly motivated by Feynman in 1982. He was mainly interested in simulating physical systems, which is probably the killing up of quantum computing technologies. The idea was back then that simulating, n-qubit quantum systems was pretty hard to do on classical computers, but simulating dynamics on quantum computers in principle should be efficient under certain assumptions, certainly. And but it was later, that the field pretty much gained momentum, and it was based on problems which were totally different for the from the simulation of quantum systems. And like, for example, Peter Shor's algorithm discovered quantum algorithm for efficient factorization of integers that had applications in cryptography. And then, of course, you probably were of the work by Grover on unstructured search when he showed that there was a polynomial speedup. But this talk is beyond these problems, right? And we are mostly interested in devising other quantum algorithms for other linear algebra problems. All right. So let me introduce the problem of linear equations. As you know, this is a very important problem in many scientific and technological applications. The problem is easily stated. We are given an n times n dimensional matrix A. Think of this big N as being huge, okay? And the goal, there is a vector B that is n dimensional, and the goal is to find X, the solution to this system, linear system. This could be done by simply implementing the inverse of the matrix A to the vector B, but that classically, of course, has a cost, which will depend on the dimension of the matrix. There's a huge number of classical algorithms for this problem. Different algorithms work under different conditions. For example, sparsity. If the matrix A is sparse, then you can take advantage of that. You probably will never want to do really all the n-square operations for doing this matrix vector multiplication, so that can be reduced. But typically, if we are thinking about exact classical algorithms, where we do exact arithmetic, the expected cost or complexity of those algorithms will be at least linear in the dimension of the matrix, even if the matrix is sparse. All right? So this is a well-known result in the field. This is HHL algorithm. HHL stands for the authors of this paper. And what the authors showed is that there is a version of this problem that I will explain more later, for which quantum computers can prepare a quantum state that encodes the solution of the vector X, right? So it's proportional to the solution of the linear linear system, and the complexity of that algorithm under certain assumptions on the matrix A, which are not too strict perhaps, is polynomial in the condition number of the matrix, polynomial in the inverse of a precision parameter, okay, because we'll do this approximately, and is polynomial in the logarithm of the dimension. So if the matrix is well behaved, so the condition number is not too large, right, and for say constant precision, then this algorithm, the scaling mainly depends on the logarithm of the dimension, which is in principle sounds like an exponential improvement of classical algorithms for this problem. Although we are, as I said, we are trying to solve another version of the problem that we'll describe later. Okay. We call this problem the QLSP, for quantum linear system problem, and yeah, so under the assumptions that I said, and under this different version of the problem, we don't know much about classical algorithms. What is the complexity of classical algorithms for that version of the QLSP? But what we do know is that, in general, the QLSP under certain assumptions is QP complete, so we wouldn't expect classical computers to simulate all instances of this problem efficiently. All right, okay. So let's talk a little bit about the assumptions, which, as I said, perhaps are not that strict. So we have the linear system. We will assume that A is a Hermitian matrix. Okay, it doesn't have to be, but if not, we can modify the problem such that it is. We will assume that A is sparse, so S will be basically the number of non-zero elements per row or column of the matrix. A will have to be invertible. Otherwise, we won't be able to solve the system unless we work in particular subspace. But for now, let's assume that A is invertible and it has a condition number. That the condition number basically tells you how far you are from being, in the non-invertible case. So that condition number will be lower than infinity. If it would be infinity, then we would have 0 eigenvalues for the matrix, and that would be invertible. And we'll assume, for example, that the largest eigenvalue of A, absolute value, will be bounded by 1. So the norm is bounded by 1. Excuse me. We will define two quantum states. One will be a quantum state B that is proportional to the vector, okay, for the linear system. By proportional, I mean that we will encode the amplitudes of the vector in this quantum state. It's a superposition state over computational basis states, and it has to be normalized, okay? And we will define another vector, which is the one that we want to prepare, the vector x, that, as I said before, this is proportional to the solution, okay? So these xi's are basically the components of the solution of this linear system. And it's also normalized. All right. So typically what we will assume is that there is an operation or a black box that I call use of A that runs in some time TA. This could be like the gate complexity, for example, of this black box, and computes the entries of the matrix A. So this is if we work in the query model. I won't go into too many details about how we query a matrix, but those details are in our papers. Okay. I will also assume that there is a black box UB, so this is a unitary procedure that runs in time state TB and prepares a quantum state, B, the one that is proportional to this vector here. For the sake of this talk, I will, rather than work in the query model, because I will reduce the problem to a Hamiltonian simulation problem at the end, I will be basically interested in what is the complexity of simulating evolutions under the Hamiltonian A, it was a Hermitian matrix, for time t and within some precision that is epsilon. Okay, so most of the complexity will be stated in terms of this quantity here. So the goal of this QLSP is basically to prepare a quantum state that I call x tilde here, which is pretty close to the state that is proportional to the solution of the system, within some precision epsilon. We want this with large probability, say, and when we succeed, we have a guarantee that we succeeded, basically. So there is a flag that indicates success, okay? So this is the goal under these assumptions. I will also change that goal a little bit, but it doesn't really change things, in which at the end, what we want to prepare, instead of a pure state, that was close to the solution, we will prepare a mixed state, okay, that is close to the solution. So perhaps we have an ancillary system, and when we trace out the ancillary system and we look at the state of the system, say, that's a mixed state, but it's not too far from the solution of the problem. So this is good enough if, for example, you are interested in computing expectation values on the state X, right? So then you could compute expectation values on the density matrix rows of X within some precision epsilon.
So this is conditioned on the success flag.
Yeah, so for this case, I mean, I can guarantee that the probability is 1, basically, for preparing this. Okay, in the previous case, the probability was greater than 1/2, so you needed to know whether you succeed or not. All right. So far, so good? Yeah, okay. All right. So, yeah, a note. What is this complexity of Hamiltonian simulation? Well, if the matrix A is sparse, there's been a lot of progress recently. I mentioned a few papers where, Andrew, myself are authors, and there's been more work recently and so on, where this complexity, right, if you want to know what is the number of queries you need to simulate the Hamiltonian A, the evolution of Hamiltonian A for time t and epsilon, it's pretty much linear in the evolution time, in the sparsity, in the complexity of querying the entries of the matrix, and pretty much linear in the logarithm of the inverse of the precision parameter. Okay, so these methods are pretty good. The scaling in precision is particularly, significant improvement from previous work. All right. Okay, so why are we interested in this problem? And that is kind of like a question that I asked yesterday when, they asked me to stand up here. So, I mean, we don't really know, but there's been some applications after the HHL algorithm where, myself and others showed that this could be useful for something. So, for example, there's a paper about computing the resistance of a network. I will make some comments a little bit afterwards about that, where this algorithm could be used. There's a paper by myself and nearby Harry where we showed that we could use this type of algorithm for computing or estimating the heated time of a classical Markov chain. Okay. In machine learning, there's a paper by Nathan and others, for the least squares problem, basically, where the problem reduces to implementing the pseudo inverse of some matrix, basically, and other work also by Andrew and Dominic Berry and others, and on solving certain linear differential equations where inverting matrices, applying the inverse of a matrix to a vector is useful as well. So in terms of the speedups, right, so I said, well, this seems great because the complexity in dimension, in principle is logarithmic, so it seems to be like an exponential improvement. But when you really go to the details of many of these algorithms, we end up most likely having polynomial speedups, okay? And this could be because of the initial state preparation, or because under the conditions that, for the particular problem, then we could probably find even faster classical algorithms that do the job as well. So as far as I know, we do not yet have any exponential speedup, quantum speedup that uses this algorithm for inverting matrices. And it could be great if we do so in the future. At least for problems of interest. Certainly the problem is, as I said, is BQP complete, so I mean, I could map Shor's algorithm to this, but it's not a natural thing to do. All right. Okay, so a little bit about the history of this. So the HHL algorithm in this paper, is a quantum algorithm that solves the QLSP and has complexity that is basically linear in the condition number of the matrix. Okay. This is the cost of preparing initial state B. And then it also depends on the complexity of simulating the Hamiltonian A for time that is also scales with the condition number, okay, and for some precision that is epsilon over the condition number. So when we look at this, there is a condition number in front of this quantity, and as I said, this quantity here is is almost linear in the evolution time. So this whole thing scales with the condition number square and is polynomial in the inverse of the precision parameter. Excuse me. But the dependence on complexity dependence on the dimension is small. Again, it's logarithmic in the dimension of the matrix. There's been further improvements for the HHL algorithm. There is this approach by Andres and Bainis, where he basically reduces the complexity to something that now it looks more linear in the condition number. This kappa is not in front of, it's not multiplying the cost of evolution with the Hamiltonian A. It's only here. But this is almost linear in the condition number over the precision cube. Okay? And yeah, as I said, if we use the best Hamiltonian simulation methods that we know up to date, this is almost linear in the condition number, where this is almost quadratic in the condition number. All right, so I mean, for the sake of completeness, I will describe a little bit how the HHL algorithm works. So there are 3 registers. I can see from here. So one will be the register that will encode the state, basically at the end. Another, used for eigenvalue estimation. Another one that indicates success, basically. So the idea is the following: that if these guys V sub I are basically the eigenvectors of the matrix A with eigenvalues lambda I, then with no loss of generality, I can write my initial state B as a linear combination of these eigenvectors here. The next step will be to use phase estimation to estimate the eigenvalues. So if I put this as an input state for phase estimation, then in another register I will have a quantum state that, this is a very rough explanation. I don't want to go into details because the whole analysis is pretty technical, but there will be another register here that kind of encodes a quantum state that has information about an estimate of the eigenvalue, okay, of the vector. This is what phase estimation does. So for this problem, it is enough to estimate each of the eigenvalues within relative precision that is order epsilon, okay, for overall precision epsilon at the end. So to do that, phase estimation has to be run with a number of qubits that depends certainly on the, in the ratio of the condition number to the precision, and it's logarithmic on that. The next step is basically conditional on this quantum state, right, to perform, a rotation on an ancillary qubit. And that rotation is made such that one of the amplitudes basically is what it's doing is applying the inverse of the matrix. Okay? And this step can be done, with a number of arithmetic operations, but it's pretty efficient. As I said, this is a very rough explanation because in principle this is a superposition state, so there's a subtle thing going on here, but let's not mind about that right now. Then we undo the phase estimation step, and then we use amplitude amplification to boost up the amplitude of the correct part of the state towards something that is a constant. All right. So we can roughly analyze the scaling of the HHL algorithm by looking at something that looks pretty much like the worst case. So this worst case could be, the initial state is a linear combination of 2 states, one that lies, at exactly one eigenvalue, the largest eigenvalue you can have for the matrix, and another one that is for the smallest eigenvalue. And the amplitudes are roughly order 1 and roughly order 1 of the inverse of the condition number. So if we apply the matrix, the operation 1 over A to this state, right, then you could see that, well, we will reduce basically the norm. For this particular case, we will increase the norm of this guy, so both states are pretty much equally important in this linear combination. So that's one way of seeing that this is kind of like the worst case. So as I said before, for the desired precision, we need to evolve with the matrix A for some time that is order kappa over epsilon. And if we do, that already introduces a complexity, that is linear, at least linear in the condition number. And if we apply the action, if I apply 1 over the condition number times A, we can't apply anything else because the norm of the operator that we apply to this state has to be bounded by 1. Then the amplitude, right, of the whole state, the norm of the whole state is getting reduced by 1 over kappa, 1 over the condition number. So since we have to apply amplitude amplification now, then we will need order of the condition number steps, rounds for amplitude amplification to boost up the amplitude towards something that is close to 1. So from here, we see that overall we need to evolve with Hamiltonian A, right, for time that is at least quadratic in the condition number over the precision, right, because of these two steps, here and here. All right, so how can that time be improved? Well, there is this idea of variable time amplitude amplification by Andres, and that's, again, it's a very technical work, so I will very roughly explain how the idea works. Yes?
Why are you evolving with A instead of A inverse?
Yes, so because we are doing phase estimation, right, for the eigenvalues of A, and then we apply conditional on the eigenvalue. Yeah. All right, so again, here are the steps, but I'll tell you a little bit, how this works. So, it is nice to have in mind, again, the worst case, right? So the idea is that the first thing that we will do will be to separate, basically the eigenvalue regions to which the eigenstates in this linear decomposition belong to. So for that, we can do a pretty bad phase estimation to distinguish, what are the large eigenvalues from what are the small eigenvalues, all right? So that doesn't have, a very large cost. In principle, ideally it could be done with constant complexity as well. So we do that, we run phase estimation. Now we can say, well, we label this as being the large, eigenvalue component of the state, and this is small eigenvalue component of the state. And then what we do next is, since we have to apply, we can only apply operators whose norm is bounded by 1. We apply the inverse of, this guy, the condition number over A, maybe using phase estimation or whatever technique, as we explain later, to the eigenstates of large eigenvalue. Okay, so we do that to this part of the state only, and that will reduce basically the norm, again, the amplitude by the condition number. So the next step is to do amplitude amplification. We send the whole thing towards basically amplitude 1. And then we apply the inverse of the matrix to the component of the eigenstate that has basically small eigenvalue. But for that, if we apply this guy, since the eigenvalue will be order of 1 over kappa, then that will not reduce the norm. Okay, so basically what it's doing is like, we apply the inverse of a matrix to a part of the state where the eigenvalues are large. We do amplitude amplification. Then to the other part, we do amplitude amplification and so on. So it's a bunch of amplitude amplification, concatenated steps and with a sequential implementation of the inverse of the operator. So at the end, because all this is pretty much sequential, well, it turns out that everything works out. It's not easy to prove, but the complexity, the overall complexity is dominated by the condition number and not the condition number square. All right. Okay, so how am I doing time? Okay. Okay, cool. All right, so for the rest of the talk, I will present a couple of algorithms, or maybe 3 algorithms, for this problem that improve previous results by HHL and Andres in several ways. So first, I will describe a quantum algorithm that runs, again, in time that is pretty much quadratic in the condition number, but whose dependence on the inverse of precision is only polylogarithmic. Okay, so that is an exponential improvement in terms of that parameter. And it turns out that our algorithm is also suitable. I mean, we could use variable time amplitude amplification on top of our algorithm to get to a scaling that is almost linear in the condition number, and still preserving the polylogarithmic scaling, the inverse of the precision parameter. All right? So I will give roughly, the ideas of how this works, since, again, all these works are highly technical. So why is this important? Well, that's a good question. So at least I know of one result by myself, my student, where we used the results of the previous algorithm to prove this speed up in terms of estimating the hidden time of a Markov chain. Okay, so this speed up is polynomial, and the fact that we have a small complexity dependence on the inverse of the precision parameter is important for this problem because the overall scaling at the end for estimating expectation values is goes with 1 over epsilon, okay? If we didn't have this improvement, then it would have gone with higher powers of 1 over epsilon, and classical algorithms do pretty well and, right in that regime. I will present another algorithm that, as I said, is based on adiabatic evolutions, and basically, it really turns out to be an evolution with Hamiltonians that depend on the matrix A, projectors on the initial state, and other Pauli matrices for ancillary qubits, where the evolution time is almost linear in the condition number of the precision parameter. So when we use Hamiltonian simulation methods, this pretty much turns out to be a complexity that is almost linear in the condition number and on the inverse precision parameter. So the method is very different from the previous method that I talked about. It doesn't use phase estimation or doesn't use variable time amplitude amplification, so it's pretty simple in some way, as you will see. So why is that result important? Well, it turns out that phase estimation, variable time amplitude amplification require a bunch of ancillary systems to be implemented. So this approach, adiabatic-like approach, doesn't use those ancillaries. And yeah, I mean, that was funny. But we posted the paper, and within 2 weeks, there was a group in China that implemented this in NMR, and they claim that this is so far the largest QLSP being solved. And the reason for that is because we don't require that many ancillaries, right? It can be running pretty small or smaller, quantum computers. All right. Okay. So this is the first algorithm. So, yeah. So recall that our main goal, the QLSP, can be achieved if we implement the inverse of the matrix to the initial state, right? Or up to norm. That has to be normalized. So what we did was the following. So in principle, this 1 over A is not a unitary operation. And with quantum computers, we can implement unitaries. So we looked at, basically an approximation of the inverse, inverse function in terms of unitary or exponentials, imaginary exponentials. Okay, so we did this through the Fourier transform. So this identity is pretty easy to prove. This turns out to be the first Hermite function, if you know this quantum harmonic oscillator. So this is what it shows there, and it's simply to obtain the Fourier transform of that function. So at the end, I can write 1 over x as a linear combination of basically these exponentials, right? So the next step is, again, is to replace x by the matrix. So now it's going to be a linear combination of evolutions under the matrix A. So there is a number of approximation steps where at the end we will have to discretize these, these are integrals, so we will have to discretize the problem because we have to encode it in, quantum computer, basically where the Hilbert spaces are finite and we use qubits. So, this is type of the approximation. So perhaps, I don't want you to keep in mind all these constants because it's going to be hard. But basically what it's saying is there is a way of approximating the inverse operator, but it's a linear combination of evolutions under the Hamiltonian A. And certainly, the number of terms that show up here and these, the spacings that we use in the discretization and so on, will depend on the condition number, because this function goes to infinity if the eigenvalue goes to 0, but we are not in that case. Okay, so that's why we can have a final linear combination here. Right. So now we are a step closer. We went from not being unitary to being a linear combination of unitaries. Right. Okay, so this is basically the idea. If I were to plot this function, if I choose whatever, the right constants here, the right parameters here, and this is the inverse function, this is how the approximate function looks like. All right? So it approximates very well the inverse up to some point in which I probably don't care anymore because I don't have eigenvalues, for the matrix that are basically below that, and then, it approximates on the other region as well. So we are good, right? And we had a good approximation to the operator in the region that we want to. All right, so certainly the accuracy of the approximation will depend, as I said before, on all these parameters that are in this linear combination. So what we do know, and this is again an analysis in our paper, is that we can choose this our J here, to be almost linear in the condition number of precision, the K almost linear in the condition number, and the things depend on, again, on precision and the inverse of the condition number. But if you look at this, right, that will turn out to be the evolutions under the Hamiltonian A, and you look at what is the maximum value of that argument that shows up there, will be related to the maximum evolution time with the Hamiltonian A. That basically goes linear in the condition number up to some logarithmic factor, all right? So remember, we want to keep this logarithmic factor in the inverse of precision, so nothing can blow up, nothing can be polynomial in 1 over epsilon. All right, okay. So what we will do for this approach is basically to reduce the QLSP to the Hamiltonian simulation problem. As I said, we approximated this by a linear combination of unitaries that in principle we cannot implement on a quantum computer, but now I will show you a way to do it that will use amplitude amplification. So suppose that we have two unitary operations, U1 and U2, and there is a linear combination that we want to implement. Lambda 1 and lambda 2 may be positive values. And we want to implement this to some state psi. So one way of doing this, we use a generalization of this in our paper, is the following. So you have the state psi, now you add an ancilla. The ancilla is initialized in 0. Then you apply a unitary that encodes basically the amplitudes, right, that show up in this linear combination, the square root. Conditional on that state, we apply either U1 or U2. And then we do the inverse of this 1 qubit operation here. And if you look at the final state, it looks like something like this. There is the right linear combination of unitaries applied to the state with an ancillary state that flags basically that the correct answer plus something that is, it's not what we want. And again, but the ancillary state is in 1. It's something orthogonal. So now what we can do is basically, that's the correct part and incorrect part. We can use amplitude amplification basically to boost this up towards 1, okay, towards something that we want. And this simple idea can be generalized to more general linear combinations of unitaries, okay? By introducing now perhaps more ancillas, since we will have to encode more amplitudes in the linear combination. And what turns out to be is that even if these lambdas say they are positive and non-normalized, they add up to some big lambda, okay? This lambda's I. Then, this idea can be generalized to prepare a quantum state. Then I have the right linear combination of unitaries applied to the state, okay, with something that flags the success of that. And there is a normalization factor that goes with the inverse of the sum of the amplitudes, right? And then something orthogonal. And this orthogonal is flagged by the state of the ancilla being orthogonal to the all zero state. All right, so again, we do amplitude amplification on the right part of the state, and then we get what we want. All right, so what we will do is basically use this linear combination of unitaries approach to implement the approximation of 1 over A that I showed before. So, in my complexity basically results, I'm kind of like hiding under the rug the complexity of implementing other operations like this V operation, because I'm assuming that that's basically fairly small compared to any other complexity that shows up in the problem. So if I look at the linear combination of unitaries for the inverse operator, it turns out that when I add up all those coefficients in the linear combination, those turn out to be very close to the condition number for this particular problem, all right? So that, as I showed before, we have to do amplitude amplification, right? So that amplitude amplification will depend on, what is the norm of the right state that I need to boost up towards 1. So for this case, this condition number will also match the number of runs of amplitude amplification steps, because that's the increase that I need on the amplitude of the state. So then when we look at the overall complexity of this approach, well, basically we'll scale in this way. So remember, I told you that we had to evolve with the Hamiltonian A for some time that was almost linear in the condition number up to some logarithmic factor, right? But now I need order condition number of steps to boost up the norm towards 1. So at the end, that enters as a multiplicative factor, with this. And because the number of amplitude amplification steps also relate to the number of initial state preparations that I need, then the complexity with basically the preparation of the state B will be multiplicative factor of the condition number with that, right? So again, this is almost quadratic in the condition number, right? Because this guy is almost linear in the condition number. And, but the complexity in terms of the precision parameter is always polylogarithmic, right? I mean, I never showed you any 1 over epsilon, any polynomial in 1 over epsilon. Everything that, wherever epsilon was always, inside the logarithm. So the next question is like, can we improve this towards something that is closer to linear in the condition number? And the answer is yes. And again, the new idea uses the approach by unbindings in some way of variable time amplitude amplification. We had to do some tricks and some modifications of it for this particular problem because variable time amplitude amplification uses phase estimation heavily. So we want to avoid that because anytime that we have phase estimation, the complexity in terms of the precision parameter is polynomial. Okay? All right. So, okay. So, as I said, variable time amplitude amplification relies heavily on phase estimation, but it turns out that for our problem, we don't have to run like very precise phase estimation. So that's the way that we get around complexities that are polynomial in the verse of the precision parameter. We only need to be able to distinguish regions of eigenvalues with high confidence, okay? And those regions depend on the condition number, but not really on the precision parameter of the problem. So, okay, so, certainly the algorithm is highly technical, but basically what we do is to replace, the rough idea is to replace every phase estimation subroutine that Andrew is using his paper to estimate the eigenvalues, right? And to implement the inverse of the operator. But now applying the inverse operator by using this linear combination of unitaries that I showed before. So again, we do this, roughly for eigenstates that belong to eigenvalues which are large. Then we run amplitude amplification, and we keep doing this for other regions of eigenvalues as well. All right. So when we put everything together, it turns out that now this complexity of evolution evolving with the Hamiltonian A, rather than having doesn't have the multiplicative factor of condition number anymore. So this complexity is almost linear in the condition number. All right, if we use the best Hamiltonian simulation methods. All right, so now I will talk about the second algorithm, and I think I'm fine. Yeah, okay. All right, and as I said, this is an adiabatic spiral approach. I mean, if you could implement this adiabatically, great, but typically we won't, right? We will have to resort to the gate model at the end. But anyway, so the motivation is clear, and then you see how things work out. All right, so the simple idea is the following. We will want to prepare, in this approach, in this adiabatic approach, we want to prepare the eigenstate of certain Hamiltonian, okay? By doing like a sequential preparation of eigenstate of Hamiltonians which are nearby. So there is like a path of eigenstates that is continuously related. And we want to target one particular eigenstate by doing like a sequential preparation of other eigenstates. I will explain this in more detail. I mean, the goal, of course, will be that that eigenstate encodes the solution to the problem, right? I mean, it has the solution to the QLSP in this case. So let's look at the system of linear equations, right? So we started with something that said, well, AX was equal to B. So now this is simple. If I were to apply the projector that is orthogonal to the vector B, right, then I have this identity. Right? On the right-hand side, I'm annihilating the state, basically, so I have 0. And so basically what it means is that this operator acting on the solution, it has to give 0. Now this guy is not Hermitian, okay? And since this algorithm will be based on the Hamiltonian-based model, then I need to build, Hermitian operators. So the simple idea is now to say, well, if I call this guy B, this operator B, let's apply B dagger B, which is now Hermitian to X. And that will give me 0 because this guy already acting on X is 0, okay? So stop me if there's something confusing, but this. So far so good? Yeah? Cool. All right. So there's a few properties that can be shown, and it's not that hard. So one thing is that, well, certainly X is a ground state of, if I call this Hamiltonian H, B dagger B, is a ground state of this because it's semi-definite positive, right? By construction, B dagger B is already semi-definite positive. So this has to be a a ground state, the lowest eigenstate of eigenvalue 0. It can also be shown that it's the unique one, okay? Because there is a unique solution to this linear system, so it has to be the unique ground state. It's a little bit more involved, the proof, but that can be shown. And the other thing that can be shown is that the next eigenvalue of this Hamiltonian H, beta B, can be shown to be, order that is on the inverse of the condition number square, all right? And for that, you can use some, results on semi-definite positive matrices to prove that. All right. So far what we did was to show that there is a Hamiltonian, okay? That is this beta B that has X as ground state, eigenvalue 0 eigenstate, and any other eigenstate lies along, there's a spectral gap, eigenvalue gap that is order 1 over kappa square. So now, if you heard about adiabatic, you know that somehow we need to find an interpolating path, right? Because we want to prepare now, say, the ground state of this Hamiltonian, but that's hard to prepare. So we want to start from somewhere that is easy, something easy to prepare, and from that state evolve it towards the state X that will have the solution of the QLSP. All right, so let's assume for the moment that the matrix, as I said that all, the condition number was kappa, but I never assumed that the matrix was positive. But let's assume for now that all the eigenvalues of A are greater than 1 over the condition number, and they go up to 1 since that's a bound on the norm, right? So the other case when A could be, could have positive and negative eigenvalues can be treated similarly, and I will explain how. So I want to define like an interpolation matrix, basically, that is the following for that case. So this A of S interpolates between the identity matrix, where all eigenvalues are 1, towards the matrix that we have, okay? So when S is equal to 0, we are in the identity case. When S is equal to 1, we are, in the case that we want to solve. Now I will define this interpolating Hamiltonian by basically replacing this A of S in my definition of B, right? So B of S will be this guy now. So this Hamiltonian now goes, from S equal to 0 to S equal to 1, and for S equal to 1 is the Hamiltonian that I had in the previous slide. If you really look at this is kind of like solving more and more difficult, linear systems as S increases. I start from something that is kind of like identity acting on the vector X equal to B, so the solution is trivial, it's just B, to something that was AX equal to B, all right, as I change my S. So, and now if I look at this Hamiltonian, I look at the lowest eigenvalue eigenstate for this that has eigenvalue 0, right? Since I only replace the matrix A, then basically the solution, the ground state for S equal to 0 is my state B. And as I change my parameter, I go through a path of ground states until I get to the solution of the problem for S equal to 1, all right? And this is Hamiltonian. Initially, it's just a project on the, orthogonal project on B state, and this is finite Hamiltonian, which is the one that I showed in the previous slide. All right, so again, the minimum eigenvalue, if you know about adiabatic, you know that the eigenvalue gap of these Hamiltonians play an important role on the complexity of the algorithm. So that's something to look at, and as I said before, the minimum eigenvalue gap is order of 1 over the condition number square. And the reason why that's the case is because if you look at the condition numbers of the matrix A of S along the path, well, that goes from something, that is 1 towards something that is the worst case of 1 of the condition number square. So you could expect that the smallest spectral gap, eigenvalue gap, is reached at the end. Furthermore, if you look at the path of this path that basically the eigenstate traverses, that I call L, you can show that there is only polylogarithmic in the condition number, right? So there is no polynomial scaling in the condition number. So that's a pretty short path, to move along. And the proof is again in our paper. All right, so there is this, version. Oh, I should have put the reference here. But there is this version of adiabatic. It's kind of like a version of, adiabatic quantum computing, but it's slightly more. There's slightly more steps, but allows us to prove a better upper bound on the complexity time that we call the randomization method. So rather, in adiabatic evolutions, basically what you do is you turn on the parameter S continuously in time, and you go very slowly, and that how slow depends on the spectral gap, okay? So the randomization method is very similar, but what you do is rather than changing the parameter continuously, you change it discretely. So there was that parameter S, you increase it a little bit, right? And now you work with the Hamiltonian for some time. That time turns out to be, has to be chosen randomly, okay? And has to be chosen randomly. It can be chosen from the uniform distribution between something that is 0 to something that depends on the inverse of the spectral gap at that point. And then I choose my parameter S a little bit more, and then I evolve for another random time. And I keep doing this. So if you do that, it turns out that, one can show that each of these steps is basically simulating like a projective measurement, okay? And if you do like, a sequence of measurements at points which are very close by, there is this idea of the quantum Zinn effect that you will be projecting the state to the next one with very high probability, all right? So certainly, I mean, the randomization method, if I were to explain that, that would be for another talk. But that's basically the idea. It's like simulating a sequence of projective measurements of the eigenstates, and I do that by evolving with the Hamiltonian for a random time. The maximum evolution time it typically depends on the inverse of the spectral gap of the Hamiltonian that step. And you can prove that if you do that, then if you started from the eigenstate B, which was the initial ground state, and I did a measurement nearby point, then I would be projecting to the new ground state with high probability and keep doing this, such that at the end, I prepare the final quantum state with high probability. Since I never really, detect whether I prepare the eigenstate or not, I keep doing this, right, by doing evolution randomization. Basically, what I do prepare at the end is a mixed state that can be shown to be epsilon away from the pure state, all right? Okay, so it turns out that for this randomization method, if you look at what is the complexity of it in terms of what is the total evolution time or what is the expected evolution time in this case, then that scales pretty much with something that depends on the length of the path square, okay, over the precision parameter and the minimum spectral gap along the path. So this is a better upper bound than the one that you obtain via adiabatic approximations. Perhaps the scaling with epsilon, can be done better in the adiabatic theorem. But in terms of the gap, we just have, the inverse of the gap. And I say better because in many problems, the path length is independent of the spectral gap, right? So, adiabatic approximations typically depend on the inverse gap square in the inverse gap cube and so on. And that would ruin our final scaling. All right, okay. So if I were to plug in everything for the problem that I just showed, well, I said that the spectral gap was going with the inverse of the condition number square, so there will be a condition number square here, and the path length, I said that it was logarithmic in the condition number, so the total evolution time with those Hamiltonians is basically what is shown here. It's almost quadratic in the condition number. All right. So that's for my 15 minutes. All right, so, so how can we prove that? Well, we could improve that if we were to use other Hamiltonians where the spectral gap were to be bigger than 1 over the condition number square. And for that, we use a technique that is called spectral gap amplification. And instead of using our Hamiltonian h of s, we now use a different Hamiltonian, okay? Which is we need to add an ancillary system. And this B and B dagger of s are the operators that we showed before. And what you can show is that basically the eigenstate that we were following in the previous slide is also an eigenstate of this Hamiltonian of eigenvalue 0, okay? In particular, I mean, another thing that you can show is that any other eigenvalue that we had in the previous slide now maps to eigenvalues which are plus minus the square root of the eigenvalues. So if I have a 0 eigenvalue and I will look into plus minus square root of the spectral gap, then I increase the spectral gap from 1 over the condition number squared to 1 over the condition number, right? So it's simply using a different type of Hamiltonian. All right, so basically nothing changed for the eigenstate that I'm following. The path length is the same because I'm following the same eigenstate. It's just that we are using different Hamiltonian with the largest spectral gap. So if I plug that into the randomization method cost, basically now I replace the gap, I increase it quadratically, so the total evolution time is almost linear in the condition number. So as you see, I mean, this is just simple evolution with the Hamiltonian, right, for random times, and I can solve the QLSP in time that is almost linear in the condition number. For the case of non-positive matrices, well, I mean, there is a trick that one can do. You want to avoid, doing an interpolation where the matrix becomes non-invertible anymore. So that's the way to do it. Again, details are in the paper. All right. Yeah, so you may ask, okay, what if I simulate this in the gate model? Well, we can certainly use, Hamiltonian simulation methods to simulate the Hamiltonian evolution that we had in the previous slide. And at the end, you can show that for the best case, when we use the Hamiltonian H prime of S, the number of, basically, the complexity will depend almost linear in the condition number of the precision parameter in terms of the queries that we need to state B. And since we can use Hamiltonian, pretty good Hamiltonian simulation methods, then we'll have a complexity that will be also almost, for the simulation of the Hamiltonian A, that will be almost linear in the condition number of over the precision. All right. It turns out that we can also improve this to polylogarithmic scalings in 1/epsilon by using some faster methods for eigenpath traversal, but those are more complicated because they, again, use ancillary systems and phase estimation and so on. So the idea here was to get rid of ancillary systems as well. All right, so I'm done. Well, we know that quantum computer seems promising. We looked at, problems in linear algebra. There seems to be some significant speedups, but it would be nice to do more work on that. I presented a couple of algorithms, for solving the QLSP. One has the advantage that the scaling in terms of precision is much better than other previously known results. The other one has the advantage that the number of ancillary systems that we need is much smaller. But it would certainly, as I said before, it would be very important to understand the applicability of these algorithms. I think we are lacking results in that regard. Well, thank you.
Questions?
Nathan.
Just a question. So if you use standard adiabatic evolution with this, but you say boundary cancellation methods in order to boost it, I'd imagine you'd end up getting a scaling like, kappa squared plus log 1/epsilon times it, rather than over epsilon. So,
correct.
And which would also be ancillary free. So do you think that there's still some merit thinking about traditional adiabatic evolution, or do you think that likely you could get similar benefits looking at the projective methods that you've done?
Yeah, that's a good question. I don't know. What do yeah, it's a valid point that you're raising.
And then I guess a similar follow-up question.
Yeah.
I suspect the answer is no, that this would be hopeless. But do you think that there's any interesting classes of paths that you could look at where local adiabatic evolution could be used to reduce the kappa dependence?
So I thought a little bit about that, and I failed. So yeah, but it doesn't mean that there's some instances for which it could be used. Yeah.
So you were going to comment on Blooming's algorithm for estimating effective resistance?
Oh yeah. So again, yes. So in that case, classically you can also do pretty well. So the only speedup that you could expect is just a quadratic speedup. Yeah. By using, again, this idea of spectral gap amplification. That would be one approach. There may be other approaches, but yeah, there's a classical algorithm that you could also, whose complexity could be formulated in terms of the condition number in that case. And, yes, just Monte Carlo. Wow, everyone goes.
So these are all algorithms, I guess, for solving systems over C, right? Over complex numbers.
Yes.
Has anyone thought about finite fields?
None that I know of for this particular problem. Yeah, I don't know. Not to the best of my knowledge.
Any other questions?
I just responded that I think Robin Victoria's work on Boole matrices.
Okay.
So
Okay, I don't know.
He's thought about it, or he has a result?
I think his thesis contains a
Oh, okay.
factorials.
Okay.
Yeah, I don't know.
I think there's results about Boolean matrix multiplication, like this query problem, but I don't know about results for linear systems. Yeah.
Martin and I briefly ended up looking at this, and math that would be required in order to be able to invert over a finite field is totally different than inverting over the reals. So we didn't make any progress on it, at least.
Maybe with quantum mechanics with finite field amplitudes, which is in the archive, so level 1 would be able to do that.
Yeah.
Okay, great.
All right. Good. Thank you.
Rolando again.
Thanks.